Hello, everyone. We are doing lesson 5.2, the definite integral. And we are using properties of integrals to find areas under curves today. Okay, so we'll start with some notation. So the definition of the word integral is it's the area under a curve. We'll call this curve f of x from x equals a to x equals b. I'm going to draw a picture to show what this means. So let's say we have our function f of x, right? And we have these two bounds, a and b, which are x values, okay? So the integral would describe the area under this curve, so between the curve and the x-axis. So this area in yellow here, that would be the integral of f of x. And we use this kind of S-shape notation to describe this. So this is the area in yellow here. This is how we would write it. So this is the integral symbol here. And the bounds here, a and b, are written here. Okay, so those are the x values that we're doing the area between. The function is written here, and then we use this dx to represent or to tell you which variable we are working with. Because sometimes there are more than one letter or variable in the function. And so here you can look to see which variable it is. Okay, so the other thing to note is it doesn't matter which variable you're working in. So the integral from a to b of f of x dx would be the exact same as the integral from a to b of f of t dt or f of r dr. Like, it doesn't matter which variable you use, it'll be the same area at each time. Okay, so sometimes, like in a word problem, for example, we might be working with the variable t for time instead of x, but this integral would be written with the letter t instead. It would give you the same area. Okay. Now that we've gotten that out of the way, let's look at some more. Let's look at some properties of integrals. So the first thing is the sign of the area. So we say that it's the area between or below the curve, but actually what we mean by integral is it's the area between the curve and the x-axis. So if the curve happens to be above the x-axis, like where I'm highlighting in yellow here, that area is going to be positive. Okay. If the curve happens to be below the x-axis, the area that we're talking about is not really beneath the curve, it's between the curve and the x-axis, and that would be negative. The part that I'm highlighting in blue here. So your final answer, whatever wins out, like whatever, if the positive area is larger than the negative area, then your final answer of the entire area would be positive, and if the negative area is larger, it would be negative. Okay, so you would add all of these pieces together. So the total area would be this part A plus B plus C all added together. Okay, so let me just give you an example of a function where the integral, the area under the curve could actually be 0 for a non-zero function. So let's just draw the curve of y equals sine x. And let's do the area under the curve from x equals 0 to x equals 2 pi. Okay, so if you recall, the sine function looks like a wave, right? Starts at 0 here to 2 pi. So the area would be positive in this region from 0 to pi, and it would be negative in this region from pi to 2 pi. And because it's exactly symmetric, these two areas would cancel out. So when you add them together, you would actually get 0. So it is possible to have an area under the curve equaling 0 for a non-zero function. Okay, let's look at another example. So this question asks us to evaluate the area from, I'll write it out in words. So we want to find the area under the curve. I'll put under because it's not always under, it's between the curve and the x-axis, but area under the curve from x equals 0 to x equals 3. And my function that I'm working with is 1 minus x. Okay, so that's going to be a linear function. It has a slope of, this is a linear line with a slope of -1 and a y-intercept of 1. Okay, so let's draw this out and calculate the area. We're going to be able to do this one just using basic formulas for area. So it's going to make some triangles here. I'm going to draw this function out. Go 1, 2, 3, -1, 2. And here is the function. So the y-axis, or sorry, y-intercept is 1, and then the slope is -1. I didn't do a great job spacing out my x-axis there, so I'll kind of draw a straight line. Okay, and we want to find the area between the curve and the x-axis. So I'm going to highlight the part that's positive. So this part here is going to be positive, and then this part here between the curve and the x-axis is going to be negative. So we can see once we add these two together, the final answer we're expecting should be negative, since the blue part is a lot larger, so it'll have a bigger area than the yellow part. So I'll call this area A and area B. So the integral from 0 to 3 of this function, 1 minus x, is going to be the area A plus the area B that we will add together. Okay, so A and B both happen to be triangles, so we can just use the formula for a triangle to get the area. So if you recall, for a triangle, the area would be base times height. So in this yellow triangle's case, that would be 1 times 1 divided by 2. So it's base times height divided by 2. 1 times 1 divided by 2. And for the blue triangle, the base would be 2 and the height would be -2. So that's why it ends up being negative, because the height is actually negative. So it'd be 2 times -2 divided by 2. Okay, and we add those together. So we get a half in yellow and then -2 for the blue part. Adding up those two together, we get -3/2 or -1.5 as my area. So the area between the curve and the x-axis is -1.5. So before today, you might not have thought that areas could be negative, but they can be when you're talking about a graph. Okay, let's go to the next page. Okay, so here we have some properties listed. I'm gonna deal with number 1 and number 5 down below in the two examples. I'll just kind of briefly discuss these 3. The first one is very similar to the addition property for derivatives. So it's analogous to that. So when you have two functions or two terms that you're trying to take the integral of, you can just simply separate them and take the integrals separately. So we did the same thing with derivatives. Anytime you have two parts of your function that are being added together, you can simply take the derivative of them separately. Rule number 4 is very similar. Okay, if you have two terms or two functions that are being subtracted from one another, you can just simply consider the integrals to be totally separate. So that's kind of nice. The other one is the constant rule. And this is analogous to our constant rule for derivatives as well. So if you have a constant times a function, so any number could be a variable or a constant like a letter, or it could be an actual number, you can simply remove it and just multiply it to the answer, just like we did for derivatives. So I'm going to put here, these are all analogous to the rules we have for derivatives. Rule number 1 and rule number 5 we're going to look at down below. I think those ones make a lot more sense when we actually draw them out. So rule number 1 says if you're trying to take the integral of a constant, then the answer would be c times b minus a. So example 2 says show with a drawing that property 1 is true. So let's draw this out and let's just rewrite the rule here so we can have a look at it as we're doing it. So it's saying if you're taking the integral of a constant number, then the answer is going to be that constant times b minus a. Okay, so our function that we are trying to find the area below the curve for is just a constant. So on a graph, okay, we don't know what that constant is. Maybe it's 3 or 7 or 38. We don't know, but we'll just label it on the graph as C here, okay? So a constant function y equals C would just look like a straight horizontal line at y equals C. And let's say we are looking at the area from x equals A to x equals B. So I'll highlight that on the graph here. We can see that this just creates a rectangle. The area that we'd be calculating is just simply this rectangle. And the area of a rectangle is length times width. The width or the height of the rectangle here, it would just simply be C. And then the width of this rectangle would be B minus A. So if we want to do the area, length times width, so it would be C times B minus A. So then we can see this property is true. Yeah, so that's not one to memorize. That's just one to kind of be able to visualize and see why that logically would be true. Same with example 3. They're going to ask us to use property number 5 here. And again, this one is much better. It's not really good to memorize it. It's just good to be able to visualize it by drawing. Okay, so it says if it is known that the area from 0 to 10, actually I'm going to do, this one in yellow, is 17. And the area from 0 to 8 of a function is 12, then they want us to find the area from 8 to 10. Okay, so let's have a look at what that would look like. We're not given an actual function here, so I'm just going to draw a random curve and call it f of x. Okay, so let's draw what's showing in yellow here first. So it's saying that the area from x equals 0 to x equals 10 is 17. I'm going to shade it in yellow just because I've highlighted it in yellow already. I'm going to use my smaller. Okay, so this area here is equal to 17. I've drawn it above the x-axis since it's positive. Okay, so that's 17. And the area from 0 to 8 in this integral here is 12. So I'm going to draw 8 on my graph here. And I'll shade that in. So this part here that I'm shading in is 12. Okay, so that entire thing is 17. And this part here that I've shaded in from 0 to 8 is 12. Oops, I forgot the x. So then this missing part from 8 to 10, what would that be? So logically, they'd have to add up to equal 17 in total. So 12 plus something equals 17. So 12 plus this missing area that I've circled is 17. So it would have to be 5. So the area from 8 to 10, f of x dx, integral from 8 to 10, f of x dx would be 5. Okay, so again, this is just best shown from a picture. It's just logic and reasoning. So if you're asked a question like this, I would recommend you just draw it out. Okay, so that's the end of the lesson today. Just to kind of briefly remind you again, for these properties, I wouldn't recommend memorizing 1 and 5, just be able to draw them and kind of think about it logically. And then 2 to 4, you shouldn't have to memorize those either, just because they're directly analogous to the rules we already had for derivatives. All right, that is the end of the lesson.